So we are talking about the next few days. Well, I guess one more day of this. We're trying to get the molecular shape of molecules. And we're going to do these kind of little tricks, Lewis dot structures. And what we are not seeing, and we're going to end up with a lot of shapes like you're seeing up here, and we're going to have funky names for them all and things. But what we're really not seeing, I think, in my view, is all the big, heavy-duty supercomputer calculations that are behind all this. We're just kind of taking the ideas and using them to generate shapes. And we're not seeing all the calculations. For example, this is a depiction of a supercomputer calculation. And notice there's regions of blue and there's regions of red. But Aaron, just off the bat, do you recognize what molecule this might be? Water. Right, oxygen's in the middle, and you have those two hydrogen atoms. And Paul, there's these red regions and there's these blue regions. And what they're going to show, what these calculations show, is that, man, the electrons are hanging out much more often. Under what color? What do you think their convention is? The red or the blue? Yeah, he's right. I don't know how he knew, but it's right. The red. The red is where the electrons are really hanging out the most. So it's a very unequal distribution of electrons. First off, in the calculation, nobody knows whose electrons are whose. They're just there, right? But they're spending more time up here around that oxygen. And look at the water's bent, too. There's a lot of calculations to get there. And we're going to do some just quick little tricks to get the same results that these calculations were doing. Okay? But that's kind of the big picture where we're at. Now let's see if we can remind ourselves a few things. April, what is covalent bonding? What was that again? Sharing electrons. Exactly. That's what's going on here, right? We have these orbitals. Now, the orbitals to generate this model weren't hydrogen atom orbitals. They were molecular orbitals, and that's way beyond where we're at. But the orbital idea still works. Each one of these atoms has its own orbitals, right? And however you want to draw them, there's this sharing of electrons. There's these overlap. These orbitals overlap, and these electrons are shared. And that's what covalent bonding is. It only works in molecules, though. What types of atoms form covalent bonds? So if you're looking at the periodic table, what types of atoms, Priscilla? What forms molecules? It's everything but starts with an M. Nothing. No metals. No metals. Right? If you have a metal, man, they just form cations. And then you have this ionic compound. You can have the plus and the minus. So as long as you don't have a metal, you're going to form molecules. Only nonmetals. Remember that kind of stepladder thing? Kind of goes something like this. All right? So only this stuff forms molecules. Okay, only that stuff. So covalent bond formation. So here's the Lewis dot structure for hydrogen, Lewis dot structure for hydrogen again. Right? Only one valence electron. And then you combine them. Okay? And we have a molecule. So we would usually probably write it H2, but that's what it is. Okay? Kelly, does it look like that molecule obeys the octet rule? What is the octet rule? It means that every atom in the molecule has to have how many electrons around it? 8. That's the octet rule. Every atom in a molecule needs to have 8 electrons around it. Does it look like hydrogen obeys the octet rule? No. It only now this is where it's kind of interesting, I think. We would probably draw it like this, right? We're not going to be doing the dot things for bonds. How many electrons does it look like are in a bond, Eric? This thing right there, which is the same as this, but how many electrons are in a bond? 2, right? So, and whose electrons are whose, it doesn't really matter. We don't know. They're being shared. Hydrogen doesn't obey the octet rule. Hydrogen quits at 2 because what noble gas, Monica Soto Ruiz, has 2 valence electrons? Helium. Right? Helium has 2 valence electrons. But all the other noble gases have how many valence? 8. Therefore, the octet rule. The octet rule. Everything wants 8 valence electrons around it. So when we're drawing these little structures, we want to obey the octet rule. Except for hydrogen. He's happy with 2 electrons. And it's weird. These guys are shared. Right? Whose 2 are they? Well, they're shared with him and they're shared with him. They both have 2 electrons around them. Okay. What is the difference between a single, double, and a triple bond? Jasmine. How would we be drawing these things? Oh, you have 2 elements. Single bond. How would you draw a double bond? Yeah, there's 2 of them. Triple bond, 3. Which one do you think would be the strongest, Summer? Triple bond. Yeah, triple bond would be the strongest. Aaron, which one would be the shortest? I think these bonds are going to have different lengths. Would the single, double, or the triple be the shortest? Now, I want you to picture it as the triple bond, and it's the way it is. And the reason why it's the triple bond is because think of it as a spring. You have a really short, compact string that's hard to stretch. That's like a triple bond. The big, long, floppy thing, right, that's like a single bond. So the more compact, the tougher it is. The more tougher it is to stretch that bond. So triple bonds are going to be the shortest, okay, and the toughest. Okay, now doesn't always work, but pretty much 90-some% of the time, Paul, there's only 4 elements that form these multiple bonds, double and triple bonds. What's one of them? Ooh, oxygen's one. I'm going to put it right there. What's another one? Anybody know? Carbon's another one. 2 more. Nitrogen. Last one. It's, the only way I remember this is CNOS. These are the elements that can form, they can be the X, right? They can form double or triple bonds. Pretty much everything else doesn't do it. Okay, that's kind of a guide when we start writing these Lewis structures for molecules. What does it mean if we say a covalent bond is polar? Priscilla. Here's a hint. What does it mean if a covalent bond or a molecule is polar? Well, yeah, we can never add or subtract. We're going to make it an anion or cation if we do electrons. But if it's polar, that means the electrons, around the atom, are they evenly distributed? Or is one being a hog? Water is a polar molecule. And polar just means that the electrons aren't evenly distributed. They're supposed to be being shared, but they're not being shared equally. That's all. So if they're not being shared equally, that means they spend more time over here. They hang out there more often. It's going to be negatively charged. But if you write negative, that means a -1, doesn't it? But it's not a -1. I mean, -1 is like chloride, Cl-. So what they're going to do is they're going to put a little partial symbol on over there. So if that end of the molecule is a little bit negative, the other dude must be a little bit positive. Right? The other side must be a little bit positive. Okay. So that's kind of that's the direction we're headed. Sketch an arrow. Okay, now how do you know where to put the partial negative? We skipped this last time, I think. Electronegativity. Okay, Kelly, which element on the periodic table, which element is the most electronegative on the planet Earth? Now let me give you a hint what electronegative is. Electronegative is it really, really wants an electron. The most out of anything else up there. Which element is it going to be? Okay. Now, not the nobles, though, because they're happy with 8. Everything wants to get to 8. So it's going to be one of these halogens, and it's the one at the top, fluorine. Fluorine is extremely reactive. So if we want to draw our little trend, you can't include the nobles in this. You have to have your arrow end up going to fluorine. It's just the opposite of the which trend. Do you recognize it? The radius, the size trend. It's the opposite of the radius trend. Okay, here's some more talk about polarity. Here's our hydrogen molecule. And in our little quantum mechanical model with all their super duper calculations, they color everything green. Everything's supposed to be shared equally. And the reason why is it didn't have to be HH. Heck, it could have been FF. Because they're both, it's an electronegativity difference is what matters. Both fluorine and fluorine are equally tugging as hard on the electron. So FF would be nonpolar too. Nonpolar is the word to use. However, when there's an electronegativity difference, like HF, now this is dramatic. This is huge. Usually it's not that big. But there's a huge electronegativity difference. All you do is look at the periodic table and see how far apart they are. And farther apart they are, man, the bigger electronegativity difference, especially if one of them is F. So then they color the guy by the F. They're going to color him red. And the guy by the H, color him kind of blue. And they have their little partial negative and their little partial positive. Okay? Now, I've always hated crayons and coloring. And that's probably why my sons hate art. So we're not going to be doing the whole color thing. We're just going to be doing this later. Right? You're going to draw your arrow towards where the negative is, where the electrons are hanging out the most. Or you could be doing this, partial negative, partial positive. Okay. Let's practice a few here. Arrange the following in order of increasing electronegativity. Eric, strontium, calcium, rubidium. Where is this stuff? Here it is. It's down here. Strontium, calcium, rubidium. Which one would be the least electronegative? Rubidium, then strontium, then calcium. Everybody agree what he said? Betcha. RB, rubidium, strontium, calcium. Okay. How about these next 3 here, Monica Soto Ruiz? We've got selenium, arsenic, and antimony. These 3. Whoa, SB is lower though. Yeah, so SB, then AS, and then SE. Right? So from weakest to most electronegative. Which of the following bonds is least polar? Jasmine, we've got HN. Now, HN, SIBR bond, NCl bond, and NN bond. They want to know which one is the least polar. So, if it was, just back up a little bit, if it was the most polar, you'd look at the 2 elements, see which ones are farthest spread apart on the periodic table. But they want the least polar, so you want the 2 that are the closest. It'd be N and N. In fact, there's no electronegativity difference. You would call that nonpolar. Would be the correct terminology for that.
So if they're spread apart, they're polar, and they're closer to each other.
They're less. Well, it'd have to be the exact same thing to be nonpolar.
Okay, but if they're at any time that they're different,
There's going to be an electronegativity difference. Yep. Okay, how about, let's put little partial negatives and partial positives on stuff. So, Summer, what would you do for this first one, CLF? Where would you put the little partial negative? On the F. Good. And then he's got to be the partial positive. How about on the HCl, Aaron? Where would you put the partial negative? Yeah, on the chlorine. So you pick the dude that's the closest to which element? Fluorine. Pick the element that's the closest to fluorine, and he's going to be your most negative. Okay. How about Paul, the last one? Where would you put your partial negative? They're the same, so there is no partial negative. You'd call this molecule nonpolar. So it's kind of a trick question. Okay. So here's some big, look at all this verbiage to write Lewis electron dot structures. What we're talking about are, well, these things. Looks like this. Looks like this. Okay. Rules for writing those. Now, there's a lot of verbiage here. You can read it at home. Let me just point out the main points. The main points are, first you got to pick what atom you're going to put in the middle. Usually, every single time, it's the first one in the formula. Like CO2. Well, C's in the middle, right? But really, the best answer is the least electronegative element. Whatever element's the least electronegative, that's what you put in the middle. And then you put everything else around that guy in the middle. Okay? Fine. Once you did, so now you've got your guy in the middle. All these elements are surrounding it. The next job you have to do is count up all the valence electrons. Essentially, you're just making a deposit in the bank. Whatever's there, you see how many valence electrons each atom is contributing to the bank. You throw them all in the bank, right? Because nobody knows whose electrons are whose. So you throw all those valence electrons in the bank, then you start distributing them in your skeleton that you drew, and you pretty much try to make octets. And if you can't make an octet, then you can try to do these double and triple bonds, but pretty much you're only playing that game with CNOS. Okay? And remember, hydrogen is happy with how many electrons? 2. Pretty much everything else you're trying to do the octet rule. But hydrogen, he's happy with 2. Okay, so let's do a couple of these together, and then we'll have you go to the boards and pretty much teach each other this. All right? Okay, BR2. So what I'm going to do is just do the skeleton thing. Okay? In fact, we should do the skeleton thing for all these guys. How about H2S? How would you draw the skeleton thing for him, Kelly? Yeah, but what would you put in the middle? The S. Because remember that, and where you put the H's, we have no idea what shape is right now. We're just drawing Lewis dot structures. We're not at shape. Because the H is only happy with one bond, with 2 electrons. So you can't put him in the middle, ever. How about IBR2? Eric, what would you put in the middle there? Yeah, on that C.
Oh, I think ours is different.
I messed it up. I changed things, sorry. On IBR2 plus, what would you put in the middle? Well, no. What would you put in the middle for your structure? The ideas were, usually it's the first guy in the formula or the least electronegative. So just he's the first dude in the formula, so you put him in the middle. Okay. And usually what I do, I'm kind of jumping way ahead here, but I always forget this. So I'm going to start doing it early. Whatever structure I end up drawing has to be brackets with a plus, because the dang thing is a plus charge, right? Okay, so let's go way back to A here and see if we can figure this out. So Monica Soto Ruiz, first we're supposed to figure out how many electrons we have in the bank. So how many would we have? We have 2 bromines. Each bromine has how many valence? 7, so a total of 7 and 7, 14. You have a total of 14 to work with. And Jasmine, I think it's a good idea just to have a general plan, and you always follow that general plan. And without having a bond there, could the thing even be together? It just fall apart, right? So just put the bond first. That's what I do. So I connect the stuff. And then I'm going to make octets around all the surrounding atoms. Well, there's no real central dude, but I made an octet. Notice how I made an octet? That line, the bond, is really counted twice, right? If you count, if I change colors here, if you change, right, here's 2, 4, 6, 8. He's happy. 2, 4, 6, 8. He's happy. See that? So you're really counting that bond in the middle twice because they're shared. Okay, now that's, I got a mess here. But anyway, did I use up 14 electrons?
Yes.
I did. 2, 4, 6, 8, 10. I did. So we're done. Okay. How about, let's do this one, and then we'll send you guys off on your own. IBR2 plus. So, Summer, how many electrons do I have in the bank there? Bromine has 7. Now I've got 2 of them. I also have 7. But then there's a plus charge, so minus how many? It's just 1, because the charge is plus 1. Right? So it's just minus 1. Okay, so that's what? That's 20, right? You have 20 to work with. Make everyone follow that? If it would have been negative, you have to add them. You have extras. So first connect them. And then make octets around the surrounding stuff. Anything left over, put them on the middle. That's pretty much how I do it. So I'm going to connect them. 2, 4. I used up 4. 2, 4. 6, 8, 10. So make octets around the surrounding stuff first. 10, that's 12, 14, 16. Anything left over, throw it on the middle. 18 and 20. It's just kind of spread out these lone pairs, these 2 electrons, spread them out as much as you can and keep them together. Don't put dot and dot, right? And that'll help us for the next class period the most. Now you look at it. Does everything have an octet? Yeah. So we're done. Okay. So let's go to the boards and knock these out. Let's do B first, though. Let's finish B, and then we'll go on to D.
Like, when we put them together, it automatically is 2.
When you make a bond, it's 2.
2.
Yep.
Like, no matter what.
Yeah, because what it really kind of looks like, Priscilla, it really looks like this. It really looks like a dot, and you're connecting it. But that's misleading, because that makes it look like bromine has a dot. But he doesn't. They're being shared. So it's misleading to put the dots in there, I think. So let's do B first, dihydrogen sulfide. Dihydrogen sulfide. Now remember, once you make a bond with the H, you're done, right? Because H then has 2 electrons. So you quit, because he's got the same as helium. Right? So you make the bonds, anything left over, put in the middle. Only a plus if it was H2S plus, but it's just H2S. Okay. I think. So you're working with a total of 8. I think everyone's pretty much got it, right? You connect them. You have 8 to work with. Connect them. I've got 2, 4. I've got 4 left. 2, 4, 6, 8. Right? Okay. Let's do HNO2. Now it's HONO. Follow the hint. He's linear. So when you have those oddballs like that, they're always going to give them to you. HONO. Figure out what your total is and start and connect stuff. Try to make octets. So before you start connecting stuff, see what your total is. Eric, it's got to be HONO. It has to be a linear HONO, like following the hint. So connect stuff first, and then try to make octets on everything. And when you do the dots, keep them paired up. So yeah, keep them paired up. I see a lot of folks adding up to 18. I agree with that. You should be working with 18 electrons. Okay. So how many have you used so far?
2, 4, 6, 8, 9, 10.
Well, don't forget about this guy. 2, 4, 6. If you go from this side to this side, it's easier. 2,
4, 6, 8, 10.
12, 14. Keep going. 16. 18.
This is where like the double bond comes in.
Okay.
I think it adds up to 18.
Adds up to 18, but not everything has an octet.
So is an octet. So do you take one off and then make a double
So
bond?
hopefully everyone's got a structure with 18 on it, right? Make sure you have 18 first. And then you ask the question Eric was asking me, right? You've got some structure. Oh, and Monica, they don't break up the dots. They like to keep them together. So just keep them together. It doesn't matter where you put them, just keep them together. So you look at it, and not everything has an octet, right? 2. Only 2. Keep the lone pairs as 2. So you put them there, right? Keep the lone pairs as 2. So don't have individual dots anywhere. A possible thing you might have ended up with is, I'm going to copy somebody's here. Here's a possible way you ended up, like this, right? That's a possible way you might have ended up. Or you might have ended up something like erase this guy. There's a lot of different ways you could have ended up, right? Either way, you ended up in one of these kind of situations, right? Everybody agree? I got 18. Now, you ask the question Eric asked. Do I do the double bond thing? The answer is a definite yes if what? CNOS. Do you have things that can form double bonds here, triple bonds? Yeah, nitrogen and oxygen. Okay. So the trick to doing this is before you make a double bond, erase 2 electrons somewhere. Right? You're just going to move the electrons around. So you erase 2 electrons somewhere, make a bond, and see if you fix the problem. Try it. Erase 2 electrons, make a bond, and see if you fix the problem. And then you count up and see if everything has 8. Okay, now, Eric, though, nitrogen has way too many. Well, before you erase it, you see that nitrogen had 10, yeah.
So it's 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8.
Make sure you have 18 somewhere. You got to have 18. I think you lost your 18, maybe.
So you just have to make sure you have 18.
2, 4, 6, 8. 2, 4, 6, 8, 10. Now you screwed up this oxygen. Now hydrogen can only have 2, though. So don't do the double bond with the H. Okay, I think this looks good. This one looks good. But what about this guy? 2, 4, 6, 8, 10. He's got too many. So this isn't going to work. He's got 10. Yeah. Do you have 18 used up? 2, 4, 6, 8, 10, 12, 14. You only have 16 electrons.
That last one has 10.
You only have 16 electrons. You have to use 18, Summer. You have to use all 18. Okay. There's another answer. Don't erase that. See if you can figure out what the other answer is. Okay. You have 18 dots on here? 2, count. 2, 4, 6, 8, 10, 12, 14, 16. If you put 2 more somewhere, now you have 18. Which one is not obeying the octet rule? All right? Okay, let's get you started on here. Which element on my little diagram is not obeying the octet rule? N. So what I'm going to do is erase something here. I'm going to erase this one. Erase before you do a double bond. And put them there. Did I solve the problem? Does everything have an octet rule? Does everything have 8? It does. Right? That's one possible answer. There's another possible answer. Do you see what it is? Have the double bond, instead of between this N and O, have it in the middle N and O. That's another possible answer. There's 2 possible answers for this one. You have the double bond there. Two, 4, 6, 8, 10, 12, 14, 16, 18. See, so there's 2 possible answers for this one. Do you see that? Okay. So you just got to keep, it's almost a game. But just make sure that to help yourself out, before you make a double bond, erase 2 electrons and make a double bond. Otherwise, you lose count pretty quick. Okay. Let's try Cn minus. Oh, you can always do brackets. Just don't write a charge, because there's no charge on it, right? It's just HNO2. There's no charge written on it. Now, this one, Monica, E, cyanide, you have to use brackets and a -1 charge out there. So on this one, you have to use brackets in your final answer with a negative charge. Cyanide, Cn minus. Count up the total. See how many electrons you have in the bank. If you're not so sure about the last one, just ask. I can help you out with it.
Is it Cn or cyanide?
Cyanide is Cn minus. That's the polyatomic ion, cyanide.
Oh, it's a carbon and a nitrogen.
Yeah, it's a carbon and a nitrogen with an overall -1 charge. All right, but it has a -1 overall charge. So what's your total? 4 plus 5 is 9. No. -1 means it has an extra electron. So the total's 10, right? The total's 10 because it has an extra electron. So you should be working with 10 electrons. Working with 10 electrons. So get all 10 electrons on there. Try to make octets. Oh, Paul, keep them paired up. They want them paired up.
Oh, okay, so I can.
Yeah, so you can't do the individual dots. I mean, you can, but it's going to help a lot better in the next class period if you don't. Okay, so we have 2, 4, 6, 8. Good, you got 10. All right? But neither one's obeying the octet rule. So see what you can do to get them to obey the octet rule. See how this guy, keep the dots together, so put them over there. All right? So we've got 2, 4, 6, 8, 10. But neither one was obeying the octet rule. 2, 4, 6, 2, 4, 6. Can you make double bonds? Do you use 10 electrons? 2, 4, 6, 2, 4, 6, 8, 10. Yeah, you got 10. And how about the octet rule? They both obey the octet? Then it has to work. Yeah. Carbon can, well, all you do is do the octet rule. Did you figure it out? You just have to have 10 total. And you can have triple bonds. You can have triple bonds, double bonds, because it's CNOS, right? It could be, but don't use more than 10 electrons. 2, 4, 6, 8, 10. But look at that carbon. He only has 4 electrons around him.
Right. But
the nitrogen has 2, 4, 6, 8, 10. So definitely messed up. Carbon's not right. Okay. Ooh. I think Priscilla might have got it. I think Monica might have got it. All right. Do you see what's wrong? So you have to use 10. So again, start out by connecting them, and then put all the dots, the lone pairs, and everything surrounding. So I used up 2, 4, 6, 8, 10. Right? Something like that is where you got to start. You have to start here. That's how I do it anyway. And then I recognize neither one has a octet, so I'm going to erase, make a double bond. Check again. Still doesn't work. So let's try it again. Now I have an octet around everything. Right? I've got my little brackets, the -1 charge. Okay. Try COBr2. COBr2. Which element are you going to put in the middle? Now, you only make this long line thing if they tell you. Otherwise, they're expecting you to surround everything around the central atom. That's their convention. So, Monica, they don't want you to make a big long line. They want you to put everything around a center atom. What's going to be the center atom? C. It's the first one, and it's the least electronegative. So you have C in the middle. Everything should be surrounding it. Okay? You see what the skeleton has to be? C in the middle. Everything surrounding it. Doesn't matter where. Just throw them in there somewhere. But they got to be surrounding him. And there's no charge, so just see what the total number of valence are in the electron bank, and then start distributing. Okay, a bunch of people have 24. I agree with that. So you should be working with 24 electrons. You should be working with 24. Now before you do, distribute your 24 before you start making double bonds. Otherwise, life really goes crazy. And don't only do double bonds, really, between CNOS. That means this guy's if you have to. If you have to, it's here. But don't jump to double bonds. You do them only if you need to. First, distribute all 24 electrons. Distribute, again, when you distribute those electrons, good. Like Monica's got it here. This is how you should distribute those electrons. It'll be the most consistent way to solve the problems, right? Distribute those electrons around all the surrounding atoms to make octets, and if you have anything left over, you put it on the center atom. Only if you have anything left over do you put it on the center atom, okay? So now, once you've got that far, you see if everything has an octet.
Does it have to be between a C and an N or a C and an O?
Yes.
Okay, so you have to have two of them.
Yes. So C and Br, no. It has to be CNOS.
So like I can't have a double bond here between C and R?
You could if you had to, but it's not very common. And we're gonna have a much better rule next class period. Right now we're just trying to follow CNOS. Okay. Now be careful. You have to have a plus in there. Watch your count.
Oh, I have it counted.
Good. Okay. So
This one and put it right here?
CNOS,
Oh, it doesn't.
not with the bromine, with the oxygen, right? Good. I see most everyone's got it, right? You have to follow CNOS, so if you're going to make a double bond, it better be with the oxygen. Good. Very good. We've got time to do one more. Now this one's an ion, ClF2+, so make sure you get your count right. That's supposed to be a chlorine. It's a Cl, chlorine, surrounded by two Fs. Chlorine surrounded by two Fs. And it's a cation.
So it would be in a straight line.
Yeah, we don't know. We don't know whether it's straight or bent or what. We're not there yet. That'll be tomorrow or Monday. It has to be capital Fs. Well, it won't. You'll get docked. I'll cream you every time. It has to be capital Fs. Well, it has to be a small L. Otherwise, I'll knock it off. You'll lose points. Okay. 14. Okay. Now, what'd you get as your total? 20. Why do you have so many? ClF2. Today's not your day, dude. No, it's chlorine.
It's because I read it as CIF2.
Chlorine. You should have 20. 20 is your total. Whatever you get, make sure your answer's in brackets with a plus. Connect them. Make octets around the surrounding. Anything left over, put it on the center atom. Well, that worked out. It worked out great like that. Oh, good deal. No, you counted up 20, right?
Yeah.
8, 8, 16. Yeah, it works. You better ace Monday's quiz. All right, I think we're out of time, but I think I see a lot of right answers, right? Connect everything. Octets around the surrounding atoms. Anything left over, put on the center atom. He's done. Everything's got an octet. So have a good weekend.